Okay, folks, we are now at the mean value theorem for integrals. Mean value theorem for integrals. So let's do a quick review. At the bottom of the page, see if you can remember the conditions of the mean value theorem for derivatives. Mean value theorem for derivatives. There were three conditions, or two conditions, and then one thing that you had to kind of find. Pause it, give it a try. Okay, so let's see how you did. So there were two theorems, right? The IVT is the one that Corpy calls the YVT because it finds a Y value. So that's like saying if you were 5 feet tall and now you're 6 feet tall, at some point you were 5 feet 5, 5 feet 6, 5 feet. At some point you were those heights along the way. That's the intermediate value theorem. You have a point above, a point below, and you're continuous in between. So in the IVT, all you need to be is continuous. The MVT talks about rates of change or how fast you're going. So if I was going 60 miles per hour and then I went up to 80 miles, sorry. Let me try again. If my average speed was 75 miles per hour, at some point I had to be going exactly 75 miles per hour along my trip. It has to be true. So that's the mean value theorem. So for us to prove that, number one, our function needs to be continuous on the closed interval a to b. Since we're talking about rates of change, you're going to need to also be differentiable, but we're differentiable on the open interval because you can't be differentiable at an endpoint because you don't know what the other one-sided limit is. And then from there, what we would calculate is the rate of change, the average rate of change. Average rate of change, which would be f of b minus f of a divided by b minus a. And then after we figured that out, then we would make the argument, and it'll look something like this. There exists some x or c or some other letter, whatever we would use, that's in the open interval from a to b. There exists some value in here such that f prime of x is equal to that slope. So there's some place in there. So if the average rate of change was 75, like I said, then there had to be some time on your trip that you were going 75 miles per hour. All right, so what does that look like, the mean value theorem for integrals? So we remember, when it comes to integrals, in derivatives, differentiability implies continuity. When it comes to integrals, it's the reverse. Continuity implies integrable, that you could integrate it. So if you're continuous on the closed interval, there exists some number in that closed interval. So now we're talking about in the closed interval, such that the integral of f of x equals f of c times b minus a. Now, this is called the average value. So this setup, I actually don't see very often. It's this other format that I think is going to be a lot more valuable. So another way to say this is to take and try to solve for f of c. So I can rewrite this and say, okay, f of c is equal to, I'm going to divide this to the other side, 1 over b minus a. If I divide that, it's going to be on the bottom, right? Times the integral from a to b of f of x dx. I like this write up a lot better. It makes a lot of sense in my head because when we're talking about the average value, think about what this does. This adds together all of these heights, right? So, you find that area under the curve. You would take all these different function heights and you'd add them together. And then you're taking that number and dividing it by b minus a, or the length of the interval, or how many possible heights there, how many possible x's there could be. To me, this makes a lot of sense because it looks just like if I said you've taken 5 tests, figure out your average. What would you do? You'd add up test 1 plus test 2 plus test 3. Let's just say 3 tests because I ran out of room. If you've taken 3 tests, you would add those 3 tests together, test 1, test 2, and test 3, and then you divide by the interval, which is 3 tests, the total number. So B minus A represents how far those things are apart, okay? So I don't know if that makes sense, but that's what helps me when I think of the average value. I'm adding up all of my function values, and I'm dividing by how many possible function values there could be. That's the length of the interval. So Corpy, if you're watching Corpy's videos, he always writes his like this, because this really shows the sum. Remember, this little sigma thing means, this integral symbol. Think back to what we did in 4.1, I think 4.1 or 4.2. We did the Riemann sums. We added together all those little rectangles. So this is the sum of all the f values, all the heights, the sum of f. And then we're dividing it by the number of x's. So if we're going from 2 to 50, there would be 48 x's in there. So this is just the average for me. Now, I like to take this out front. I don't like this notation. I think it gets too cumbersome like this. So I take and I make it a 1 over b minus a. This is the way that you're going to see me write it a lot. So here's the idea. So we've got the curve here. This is f of x, our curve here. If I ask you to calculate the area under that curve, if I ask you to integrate it, you're going to have this. Oh, dang nabbit. This area here. Well, ignore that pretend like I didn't fill that in. All of this, I'll pick a different color. How about that? All of this that's the area under the curve. According to the mean value theorem for integrals, there's some place between a and b that if I go to that place and I track up to the function and I use that as like my midpoint or my some sort of Riemann sum estimate, it doesn't have to be midpoint. I wish I didn't say that. It's some point in between. If I use that as my height and I keep my width, I use that as my height and I keep this as my width, then these two things would have the same area. So this rectangle that I'm now highlighting has exactly the same area as the blue part that I highlighted before. Those have the exact same area. So f of c, this value right here, f of c is the average height, the average y value. If you took all these heights, all these y values, and added them all together, which would be impossible because there's infinitely many of them, but if you could, you would add them together and divide by how many there could be, that would be this distance here, you would get that y value, that height. So just to point out that this green and blue have the same area. Green and blue have the same area. Okay, so yay, yes, I always like to see that. In New Braunfels, I don't know where that is. The temperature in degrees Fahrenheit, T hours after 9 a.m. was modeled by the function blah, blah, blah. Find the average temperature during the 12-hour period, and then find the values of T such that means actually go figure out what that C value is. So we'll get back to that in a minute. Now I want to highlight something here. You've got to be careful. You got to be careful when you see the word average. There are two different types of averages. There's what's called the average rate of change. Average rate of change. And the average rate of change means average slope. This is what we did first semester. We're talking if the average rate of change, that's my slope basically. So that's where we did f of b minus f of a over b minus a. If I wanted to figure out the average velocity and I give you position, you'd do the slope. That'd be how your position changed over that whole interval. That's your average rate of change, average slope. When I talk about the average value means the average y value. So it's kind of like the average height. And we've got to find that by like literally doing the average formula. So I would take 1 over how far apart my interval is. That's kind of like saying how many tests you would take. But then I need to add together from A to B all of the possible heights that my function could reach. So be careful. Average rate of change. If I say average velocity, if I say average acceleration, if I say average position, I couldn't say average position, but average rates of change are just strictly the slope formula. Average values is where we add up all the values. These are the y values, and then we divide them by how many there were. Okay, so blah, 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 blah. Okay, find the average temperature. So the average temperature, is that a rate of change? No, it's not a rate of change. It's an average number. So I want to figure out of all the temperatures from 9 a.m. to 9 p.m., which, by the way, is continuous, so we can integrate it. Then I don't need to, I can integrate it, so then I can calculate, add them all up and divide by how many there were. So let's take a look. So I'll give you a second. I would like you to try to set up. Don't write this out yet. Just call it T of t, big T of little t. Try to write what you think the integral would look like based on that first part. Okay, so let's see how you did. I'm going to talk about an average value. So how far apart is 9 a.m. to 9 p.m.? We're talking about hours. So that's 1/12. The integral from, now look, this is 9 a.m. That's after 9 a.m. So 9 a.m. you can kind of consider to be the 0 hour. And then we go until 9 p.m., which would be the 12th hour. 10 a.m. would be the first hour. 11 a.m. would be the second hour, etc. So we go from the 0 hour, which is 9 a.m., until the 12th hour, which is 9 p.m. Now, you can write this in here if you want to use a parenthesis and write that. I'm just going to be lazy. They already referenced that was that they already said what T, big T of little t is, so I don't have to rewrite it. I can just write the name of it here. But you must write for a whole stinking point D of t here. Okay, now the beauty of this is that we can use our calculator, right? It says a calculator problem. Don't try to integrate this nastiness. You probably, I don't know. It might be pretty tough with that. Yeah, we would need to do a U substitution, which we don't know how to do yet. So we would do this in our calculator. Now, this is one that I would actually store this because I'm looking ahead, and it says find the values of T at which the MVT guarantees a temperature that's the same as the average temperature. So I'm going to need to graph this thing anyway. Instead of typing this in here into my integrator, I'm going to go into y equals because I'm going to have to figure out where this graph reaches a certain height. So I'm going to actually store this as my y1. Pi t, of course we're going to call it x, over 12. That makes sense? Okay, yeah, looks good. So now I'm going to quit out of here, check your mode. We should always be in radians, almost always in radians. I'll move this up here. Sorry, hopefully you could see all that. All right, so now I want to integrate. I got to put the 1 over 12 out there first. So 1 over 12 times the integral from 0 until 12 of, now look, if you want to type this equation in here, go for it. You can, but remember, we already typed that into our equation list as y1. So I can go underneath alpha F4, and it lists all those different equations. So if you put something in to y1 and you want to use it, just type, oh, I was in the wrong spot, but you get the idea. You can now go to alpha F4, hit y1, and it takes that equation from y1 and it'll put it in that place. Now be careful here. What are we deriving according to? Yeah, we're still deriving according to x. Y1 is just the name of the equation that we're plugging into that spot. So we plug it in, we get 58.912. Hit pause and think about what that thing represents. Okay, that represents the average temperature. So my average temp is equal to 58.912. So that's the answer to part A. Find the average temperature. So if you took all the temperatures from 9 a.m. to 9 p.m., think about there's infinitely many, but if you could somehow add them all up and divide by 12, you would get 58.92. That was the average temp. Now part B is saying something a little bit different. Part B says find the values of little t, so find the times at which the MVT guarantees that the temperature was the same as the average. So I'm trying to find little t that equals. So I want to know, when is big T of little t equal to the average temp? So in other words, we want to figure out when this is equal to 58.912. So the easiest way to do that is to do what? What could we do to this and this? Remember, we can use our calc, make life a lot easier. Okay, hopefully you said that you would graph this and you would graph this and see when they hit each other. Now, I want to make sure that I don't round when I don't want to round when I don't need to. So what I'm going to do before I move on, I'm going to store this number as the variable A. So now I've got, whenever I use A, I've got that basically exact value. It's still rounded somewhere way down there. I don't know where. So what would be a good window? Okay, so what would be a domain that makes sense? So 9 a.m. is the equivalent of 0 hour. 9 p.m. is the equivalent of 12 hour. I always like to give myself a little bit more room, so I'm going to go from -1 to 13. Oh boy, what would be a good, if my average is 58, how cold do you think it gets? Let's say 20. We'll see how it goes. 20 until, let's say 70. Let's see how that looks. I'm going to count by tens just because I'm not sure. Let's see. Nice. Okay, so that's the curve that shows us from, I'm going to adjust that window. I don't like that 0 to 12. I'm going to go exact. So this is all the temperature change that happened from 9 a.m. to 9 p.m. Now we want to figure out when this curve is at a height of 58.9, blah, blah, blah. So I'm going to go back here. I'm going to go to my second equation, and I'm just going to call that A. Remember, that's that number that we found in part A. And so when I graph it, now I've got this curve of temperature that intersects with this curve of specific temperature where their average is. So now I need to find these two values. Remember, everything good is underneath calc. Intersect, enter. I like to move the cursor first. You don't really have to, but just get somewhat close. Just get closer to the one that you want to try to find. Hit enter 3 times, and it spits back that intersection. So one of my times, let's see if I can squeeze this over here. So one of my times would be T1 is equal to 2.636 hours. Just 2 point, that would not be a good way to write it. We should try to combine that this is connected to this starting spot of 9 p.m. So 2.636 hours after 9 a.m. Now, if that was the only one, that'd be it. But the temperature goes above it, and then it goes below it again. So we want to go find that intersection as well. So I'm going to move along my curve. You don't want to move along this curve, jump to the other one, but it's not any faster Kind of feels like it is, but it's not. Get close, hit enter 3 times, and we get our second temperature. My bad. My second time, 9.363 hours after 9 a.m. So if about 2.5 hours after 9 a.m. and about 9.5 hours after 9 a.m. is when you had the temperature exactly equal to the average temperature. Okay, so down here we're basically doing what we did right here. Find the exact value of C. So we're finding these values at which the average is equal to the real function. The function is equal to the average. I don't like the way I said that. I'm trying to find this value of C when f of C would equal whatever the average value is for this curve. So find the value of C. So we need to first set up an integral. So I'm going to encourage you to pause and try to set up an integral. Okay, so let's see. So my function that I'm trying to find a function value at C. I'm trying to figure out when the curve, f of C, is equal to the average value. Well, what's the average value? 1 over b minus a. So my interval would be from -1 to 2. So 2 minus -1 is 3. I'll write this out. 2 minus -1. Just write it out for the sake of notes. Got that for my interval. The integral from -1 to 2 of, and if you want to put this in here, or if you want to call it f of x, it really doesn't matter. I'm going to put it in there this time. Do not forget your dx. That's a point in and of itself. So let's clean this up a little bit. Actually, I'm going to do both at the same time. So clean this up. That becomes 1/3. I'm going to integrate this. So the integral of 1 is x, plus the integral of x squared is x cubed over 3, which is defined from -1 to 2. Now I can start a chugging and a plugging. Plugging and a chugging and a plugging. I said it backwards. So I'm going to put 2 in there. So that's 2 plus 2 cubed is 8. 8/3. Great. Common denominators. That's going to be a lot of fun. Minus, put -1 in there. Yeah, this is going to be negative again, right? Because negative cubed is still negative. So I'm going to put that as a -1/3. Ran out of room. I don't think I'm going to be able to fit it all in here. So I got to go back over here. All right, so I got my 1/3 times, okay, 2 plus, so that's going to become, what, 6/3? 6/3, so that's 14/3. 14/3 minus, that's going to be -4/3, so that's going to turn into plus 4/3, which equals 1/3 times 18/3, which is 18 over 9. 18 over 9 ends up being 2. Notice I didn't box that in. All that work, we just now figured out that the average value of my function is 2. So between -1 and 2, my function reaches an average height of 2. Now we want to figure out what value of C actually is at that height. So now I'm going to go to my equation, and I'm going to make that equation equal this height. So f of C, which equals 1 plus, well, I'm going to call it f of x. I don't want to use C. Plus 1 plus x squared has to equal a height of 2. Let's do a little bit of algebra here. Bump over the 1. Square root, square root. Square root is on fire. We don't need no water, but we do need a plus or a minus. So, if you take the function value at -1 or the function value at 1, their heights are the average heights of all the points between -1 and 2. And let's prove that graphically. Let's show what that looks like on a graph. So I'm going to make, so this, what's our family? This is the squared family, so that's a parabola that's been shifted. How's the shift? Hopefully you said that that's a shift upward by 1. So I'm going to draw a little coordinate plane, but I'm going to be biased towards the top and towards the right, because it's going to take my parabola family, and shift it up 1. So I've got -1, then I've got 1, then I've got 2. I could keep going, but that's our interval. So let's see what our function heights are. So at -1, I plug that in. That's going to take me into, actually, let's just do it like this. What am I going to need? 2, 4, 5 of them. 1, 2, 3, 4, 5. My function reaches a height of shifts up 1, over 1, up 1, over 1, up 1, over 2, up 4. Ugh, not my best drawing, but you get the idea. Okay, so what we have just determined the area under the curve in green is going to be the exact same as the area under the curve that I find if I use the function value. Notice that these are at the same heights. If I use these function values as my height. So that rectangle that I just drew is equivalent in area to the area under the curve in green, that shaded part in green. Okay, so I'll show that the average rate of change of a car's position over time is the same as the average value of its velocity function over time, over the same interval. So I'm going to start off with this. I want to circle this, average rate of change, and I want you to write a little note to yourself on what average rate of change is, and then I'm going to circle average value, and I want you to write a little note on what those things look like. How do you calculate the average rate of change? How do you calculate the average value? Pause, give it a try. Okay, the average rate of change, that's the slope. So we would do our slope formula. You could write y minus y if you wanted to, but we're fancy now. So we do f of b minus f of a over b minus a, also known, if you remember way back, this is called the difference quotient. It's what we use to prove derivatives by definition. Okay, now the average value, if you haven't done that yet, pause and try to think. The average value is calculated by adding up all the values and dividing by how many values there were. I like to write it like this: b minus a, that's how many values there are, multiplied by the integral from a to b of f of x dx. Corpy likes to put that b minus a on the bottom. It's going to get us the same thing. All right, so for this story, we need to show that the average rate of change of a car's position. So let's let x of t equal position. Okay, so what's the average rate of change of position? Average rate of change then would be the slope. The slope from time 1 to time 2. So the slope would be x of time 2 minus x of time 1. Those are the positions, divided by how long it took. Time 1 minus time 2. And we need to show that this is the same as the average value of the velocity. So we'll use the usual notation. V of t is equal to velocity. Okay, so now I want to find the average value of velocity. So the average value of velocity is 1 over the interval, how long my interval is, so that would be t2 minus t1, times the integral from t1 to t2 of velocity dt. Okay, well, let's integrate this thing. So I've got 1 over t2 minus t1 The integral of velocity, well, we know that. Whose derivative is velocity? Position. So the integral of velocity would be position. So if x prime of t is equal to v of t, therefore x of t is equal to the integral of v of t. So if I integrate v of t, I get x of t. So this would be x of t from t sub 1 to t sub 2. Fundamental theorem of calculus means we can then plug those two things in. 1 over t2 minus t1 multiplied by x of t2 minus x of t1, which if I cleaned it up would be x of t2 minus x of t1 all over t2 minus t1, which OMG, amazing. So show that they're the same thing. So you could calculate, if you want to figure out the average value of velocity, that's going to be the exact same as the average rate of change of position. So it depends on how the question is asked. You got to be a little careful, because both of these things could be used to calculate. Let me get a good color here. So if I ask you to find average velocity, that works and that works. So how do you decide which one? Well, it depends on what you're given. If you're given position, if you want to find the average velocity, if you're given position, you'd have to do the slope of those positions, see how they're changing. If you're given two velocities, you'd have to use this formula to calculate. So average velocity can be a little bit sneaky along the way. All right, I want to do one more in this setup, or in this section. Okay, so we've got the table below gives values for a continuous function. Boom, right away. That means something. If my function is continuous, therefore it is integrable. I like differentiable a lot better than that word. All right, so we've got this continuous function. Using the values given, find the arithmetic mean of f of x. Arithmetic mean. Go back to middle school, probably actually before. Arithmetic mean is just the average. So add them all up. I don't know a nice way to do it. How can I say this? Add them all up and divide by how many? So I'm just going to call it the regular average. I don't know, maybe I'll think of a better one at some point, but it won't be on this video. So we want to figure out the regular average of this. We would literally add them up and divide by how many there are. So arithmetic mean. Uh, 42 plus 38 plus 31 plus 29 plus 35 plus 48 plus 60 divided by how many are there? 1, 2, 3, 4, 5, 6, 7. So arithmetic mean is like you'd figure out your GPA, or you're figuring out how your average is on your test scores. Add them up and divide. Yeah. I'm going to save us some time. This turns out to be 283 over 7, which ends up being 40.428. So there's my arithmetic mean. Now, the nice thing, if this was a free response, you wouldn't have to do any of that crap. Just stop. You're showing that you understand how arithmetic means work here. Now we're going to use a trapezoid approximation using 6 subintervals. Let's see if that fits with what we have. 1, 2, 3, 4, 5. Yep, 6 subintervals. 6 subintervals would be a nice use of estimate, though. Be careful here. What color would highlight that well? Be careful. This is an estimate, which means you're going to need to use some approximately somewhere in this problem. Okay, so my average, use this to estimate the average value. So now I want average value. the average value is equal to, go ahead and write out the formula again, 1 over b minus a. Oh, shoot. No, I can go right to, we know what a and b are because we're going from 20 to 50. 1 over 30 times the integral from 20 to 50 of f of x dx. Okay, and now we're going to do, how do you, that's easy, but how do you evaluate this? Well, we don't have a function, which means we have to estimate it using the table and using some Riemann sum stuff. So here's my approximately. I'm estimating what this is going to be using a trapezoid rule. So let's think back to the trapezoid rule. So first of all, trapezoid rule is going to be the width of the base. So how do we have, that's nice, we have all 5s. So our base is going to be 5 again. And let's do the 1/2. So let's do a quick review up here. Area of a trapezoid. Formula's on the, go for it. All right, let's see how you did. Hopefully you pause it and you remember this. This is not one that's going to ever be given to us. 1/2 times the height times base 1 plus base 2. Now, I usually think of this height as being the width and then these as being the actual heights. But how you think about it, that's your call. So I'm going to have a 1/2. What are my heights? Well, my heights are all a gap of 5. Now, the trapezoid rule, what's nice about this, when you have the interval, so let's take this interval. This would be base 1. This would be base 2. The next one, this would be base 1, and this would be base 2. And this would be base 1, and this. So this number here is going to get counted twice. This one won't because it's on the one end. So it's going to be 42 plus 2 times 38 plus 2 times 31 plus 2 times 29 plus 2 times 35 plus 2 times 48 plus 60. Oh, I need another parenthesis here. I almost ran out of room, but I made it. Which now equals, by the way, equals, because even though this was our one approximation, but this is no longer an approximation when I go from this line to this line. So this equals 38 2/3, which equals 38.66. I'm going to make it a 7. You know what I mean? One step away from that evil devil's number. So we use this answer would, or the 38, the mixed number would be fine as well. Either one of those are fine. You know what? Back again to the AP test for your response. Just stop at this point unless you have to actually use this number somewhere. So how close? Which one's a better? Okay, so it says which one for this continuous function is it possible to determine which is more accurate? No, we don't have enough info. We don't know what's happening in between all these gaps. Now, if we did have a fully continuous function, this one would be better. This one I think would be better. We'd have to actually know what the real average was of, what are these? Well, they didn't tell us what this function relates to.